If you've ever struggled to simulate additive manufacturing in Abaqus or didn't even know where to begin, this is the only tutorial you'll ever need. Whether you're just starting out or ready to tackle advanced simulations with subroutines, you're in the right place. We kick things off with a clean single-layer additive manufacturing simulation. No subroutine, no coding, just fundamentals done right. Then we take it up a notch by adding a second layer to simulate realistic multi-pass heat buildup, still without a single line of code. After that, we shift gears and simulate the residual stress caused by the additive process. Yes, full analysis after the thermal step. Next, we dive into arc-based additive manufacturing using powerful Goldak DFLUX heat source, perfect for modeling wire arc additive manufacturing. And finally, we go simulate laser-based additive manufacturing simulation with a Gaussian DFLUX simulation for selective laser melting, or SLM. Every step is covered from geometry to meshing, heat input to post-processing. And if you want the subroutine codes or full simulation files, just check the description. Let's get into it. In this video, I'll walk you through a unique technique in Abaqus that can give you a more realistic simulation. This technique is something that many experts are not aware of, and the best part, you won't have to write any subroutines. So let's dive in and see how this can transform your simulation. So create part. We want to create the substrate first, then we create the layer. The substrate should be 3D deformable solid extrusion. This guy can be 0.1. We create a rectangle like this and we add the dimensions. So this guy can be 0.006 and 0.05. Okay, done. And we want to extrude it with a number of 0.12. So this is the substrate. Now we're going to create the layer. So layer, solid extrusion 0.05. Now we create another rectangle. This should be 0.002 and this should be 0.012 and it should be extruded 0.04. So this is the additive layer. Now it should be divided into some parts. So partition cell, define cutting plane, 3 points. We divide it from the center using these 3 points. Now we want to divide each of them into 2 parts. So like this, and scroll button each time, you can go faster. Now we have our additive manufacturing layer divided into 4 parts. Now it's time to go to the property. Now we want to create separate properties for layer and the substrate. So I start with the layer from general density. We use this value of density. Now we can go from thermal conductivity and copy and paste these values, but first we have to check to use temperature dependent data. And from thermal specific heat, again use temperature dependent data. Now we copy and paste the specific heat and the temperature. It's better to be Inconel 738. And now we want to create one for the substrate, which is the steel. General density, we have this value, copy, paste. Thermal conductivity, temperature dependent data, thermal specific heat, temperature dependent data, copy and paste. So this is okay. Now we want to create a section. This is the substrate section, solid homogeneous. Now we choose the steel for the substrate and we create one for the layer, solid homogeneous again, and we select the inclinal 738. So we want to assign the sections, so this part, uncheck this one in order not to create too many sets. And this is the substrate. Now from here we go to the layer, we select it, we assign the layer section to it, and that's okay. So everything is done here. Now we want to move to the assembly. Now we create our instances. We first create the substrate, hit OK. Now we want to translate it to the 0, 0, 0. So I click on this one, scroll button, this point should go here, and scroll button again. So I reset this, and I want to create the layer. So this is the layer, okay, but I want to translate it. So first I translate this one from here to here, hit OK. Now from this one, query information, pointer node, I zoom in, I select this one and click OK. It gives us the coordinate. Control C, we can copy that, and we want to translate this one to here. So translate instance, we select this one, scroll button. Now I select this one, which is the center of this layer, and I paste it, but in the Z direction it should be 60. So this is 60 in the Z direction. I click enter, okay. Now we have our layer in the middle of this substrate. Now we're good to go to the next one, which is mesh. Here I would like to go to the part and the substrate. We want to create one path on this one, so I click on partition face sketch, select vertical right, and create two lines here and here, and each of them should have the distance of 0.19 from the sides. This one is okay, and this one should be okay, and this guy should be 0.012, which is the same as the width of the layer. Okay, enter, and we delete this one. Now we don't want any purple thing here. Click on down, down. Now this is created. Now it's time to sweep that. So left click, hold, and come here to the extrude / sweep. I select this one, scroll button, sweep along edge. This one, create partition. Another time here. This one, sweep along edge. This edge, scroll button, and down. So if we rotate this instance, we see this layer is extruded here. Okay, escape. And if we look at it in the assembly, you see these lines are created. Alright, now it's time to mesh this layer. See the edges. I select all of the edges, done, and by number, click on 4. Okay, done, and mesh. Now we have a mesh here, and we want to go to the substrate. Now this part is kind of tricky, so if we want to mesh this one, we should select every line parallel to the length of the layer. Okay, we select that. This value should be 48. I will tell you in a second. If we mesh and we go to the assembly, we see that each line coinciding here. This one we have 16 elements on this one, and the length of the substrate is 3 times higher than the layer, so the mesh should be 3 times higher in the number. It should be 16 times 3, which is 48. But now we want to seed the edge. I would like to delete the mesh. Now we want to rotate, select by holding shift. We can select every line, and we want to create a bias. So I click on done. We have bias, we can have single, and we want to flip a couple of them, which are these one. and done. You see the arrows should face toward the center, and we can have 5, and we mesh the part. Yeah, it's not bad, it can be better. Okay, now we have assembling. As you see, these lines should be in line with each other, which is pretty important. So the next thing is to go to the layer. Now put this one on cell and select the first cell, replace selected. So we want to create some sets. We should go to the set manager, create set 1. It should be element. We select all the elements, scroll button. Now we replace all, and we repeat this for all layers. Okay, as we see here, we have set 1, set 2, set 3, and set 4. We want to create another set. We say layer, elements, continue. We select the whole layer and we click done. Now we have another layer. Now we can go to the step, create step depth. This should be heat transfer, step depth. The time period should be a pretty small one, 0.1, and we can have 0.01, 1e minus 20, and this one 0.1 is okay, and this one should be 350. Okay, now we go to the step manager. Step 2 should be 5 seconds, and this one should be 0.01, 1e minus 20, and 2.5, which is half of the time we have, and this one should be 350. This should be 1000. We create 3 more steps which are exactly the same as step 2. Okay, the step is completed. Now it's time to go to the interaction. We want to create an interaction here from the model change in the step depth. Continue. Now we want to have this one deactivated. Put this on element. We select from sets, layer. We select all layers and we say that this one is deactivated. Now we want to create another one, model change in step 2. Again, elements. Now we want to select layer 1, set 1, and we have this one reactivated. We create 3 more interactions which are pretty much the same for other layers, and it should be something like this. As you see, if I click on this, you see which part is selected. Now it's time to create the surface film condition interaction. Okay, I put this one on cell. By holding shift, I can select this one, and I want to remove them. Now we go to the create interaction, surface film condition, and it should be on step depth. You can say surface film steel. Continue. Now we select literally everywhere and we rotate the instance. Click escape. By holding control, we deselect the bottom part. Okay, we want to select this one. The film coefficient should be 10 and the sink temperature is something like 25. As you see, the interaction is created. Now we want to select the layer, so we remove the base metal. We create another interaction, surface film condition, and we select this one. Okay, we click on done. This time it should be 242 and the sink temperature is 25 again. Okay, renamed to surface film in Cornell. There's another interaction that should be selected, but before that we want to go to the model and edit attributes, model 1. Absolute zero temperature is minus 273.15 and the Stephen Boltzmann constant is this one. Control C, Control V, Okay, now we can create the surface radiation. So let's name it surface radiation. Continue. This time we want to select everywhere but this bottom part. Okay, 0.7, and the ambient temperature we say 20. Now the interaction section is over. It's time to go to the load. So we want to create our own distribution on each layer. So we want to create some datum points. From tools, we go to the datum, midway between 2 points, we select these 2 points and we see that a point is created in the center, and we select these two. Okay, it is created. Now we want to create our own local coordinates and apply the load on those local coordinates so that we can have a distribution. So here we click on this one, we create another one. Yeah, we have our datum here. We have to do that for all other points we have here for local coordinates. Okay, now it's time to apply the load. Load 1, surface heat flux. We select this surface, we click on done, and the magnitude 1.25 E7, and here instead of the normal distribution we want to create analytical field. So analytical field, we click on continue. Now we want to input the flux distribution equation here. In this Excel file I have the equation. This is the equation in the syntax of Abaqus. Okay, we put it here, and now we want to select the local coordinate. This is the coordinate we have, and I click on OK. Now we want to select this one here. It is OK. Now we want to create other loads, and we have to keep in mind that we have to select each coordinate in each step, and we want to deactivate it, this one, after it's done. Now the steps should be like this: step 1 here, step 2 here, and make sure to select everything correctly. It should be like this. Alright, everything is almost done. Now we want to go to create a predefined field. Step initial, and it should be other temperature. We select everything and we say 25. Okay, now there are a couple of things that we should do. First, we go to step and create a cooling step. So after step 5 it should be cooling 420, 0.01, 1000, and it can be 220, 350. We click on OK. Now it's time to go to the load manager. We want to deactivate this one, and from the mesh we go to the part and we want to assign element type. Select everything, scroll button, and this should be heat transfer, convection / diffusion should be turned on, and from the substrate we do the same, heat transfer, convection, diffusion. Now everything looks good. We can go and create the job. So I would like to name it SLM, continue, OK, submit, and yes. Now I come back after the job is completed. Job is completed. Let's go to the result section. Put it on this one, and here nodal temperature, and see how it goes. Yeah, as you see, the flux is moving. In order to have a realistic one, we want to make it slower and see how it goes. Yeah, this is the movement of the flux, because we created local coordinates and also we created the expression for the Gaussian distribution, and here you see that the shape of the molten pole is visible here like this. As you see here on the last part of the step, we can go and check the temperature from here. If we go node and probe value, we can see every node we want. Here it says that the maximum temperature is 1700, while here is way different. We can also create a plot. So from here, create XY data, ODP field output, continue, and from the unique nodal, you can have the nodal temperature, and you can edit selection. So you can pick it from the viewport by holding shift, click a couple of nodes, and you can plot that. As you see, here is the plot of temperature versus time. This node has the highest temperature, and also this plot is so useful. You can calculate the cooling rate from this one. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In the previous video, we showed you how to simulate additive manufacturing in a single layer in Abaqus. Now, let's take it a step further and create a multi-layer additive manufacturing simulation. If you haven't watched that video yet, make sure to check it out first. Let's dive in. So now we open the previous file. We have it here. We don't want to mess with it, so we copy the model. We name it model 2, and we would like to go to the assembly and assemble another layer. So here, create instance, we have layer, okay, and we translate this one, click on this layer, scroll button, this part should come here, scroll button again. Now we have 2 layers, and it's time to go to step. Now we go to the step manager. This is the cooling. We want to reduce this cooling time to 30 seconds. And this one should be 15. Okay, now we want to create more steps. Time period should be 5. This one should be 1000, 1e minus 2, and 1e minus 20, 2.5, 350, and okay, we create more steps like this. And these are the steps. We want to create a cooling step as well, so call it cooling final. It should be 100 seconds. This one is 50, 1e minus 20, 1000 for this one, and 350. Let's say 50 this one. And okay, now we have the cooling step we wanted, and these are all the steps which are the same as the first layer. The step is done. Now it's time to go to mesh. As we see here, we have the second layer meshed because we basically assembled a new part, but we want to create more sets. So from here, we put it on cells. This one should be the first cell of the second layer because this is going this way. This cell goes forward through here, then come back like this. So this one is the first one. We put this one. Now from tools, set, manager, we create layer 2, set 1, element, scroll button. Now we want to do the same for other layers. Okay, we have layer 2, set 1, set 2, set 3, and set 4. Now we want another one which is all layers. So we create another one which is all layers. So we want to select all these by holding shift. We want to say replace selected, and we create all 2 layers from the element. We select them, scroll button. Now we have this one. Okay, these are the sets that were required for this, and now we can jump back to interaction. From here, the interaction manager, we want to create interactions like the previous one. So I create interaction number 6 because I want it to be in order. Model change, and it should start from step 7. Continue. This one must be element, reactivated, select here. So basically it created all different sets from the previous layer, but this is the one we created, and we click on continue, reactivated, and okay. Now we want to double check. Yes, this is the one we wanted. Now we want to create other interactions for these 3 layers. Now the interactions are created. So we basically have this one, this one, this one, and this one. Now it should be something look like this, and we want to create this step here, and this one must be changed. So from the sets, we want to select all 2 layers because we want no layers in the beginning and reactivate them one by one. Now here we have the surface film. This one is for the layers. We want to select these layers as well. So by holding shift, we can select them. Now rotating this one. Escape, holding shift, and we can select this side. Rotate again, escape, hold shift, and everything is created. Now scroll button. Done. This is the interaction we had. We want to check everything else. This is for the substrate, and this one also needs to be changed. So from pick, here we select this one. By holding Alt, Control, and the left click, we can rotate easier. So we want to select everything. We can zoom in and rotating and selecting. Holding shift, left click. Now this one is also selected. Scroll button and click on OK. Now we modified everything here, but we want to create another constraint. So from create constraint, we want to tie this layer to the substrate and the second layer to the first layer. So this is constraint 1. We can name it substrate to layer 1. Continue. We select this node region. We select this one, uncheck this one, and done. Now we want to select node region again. By clicking here, we can get rid of this one. So click on done and remove. Now we go to the under and select this one and scroll button. So we selected master and slave. The master should be the substrate and the slave should be layer 1. Okay. Now we want to create another one, which is layer 1 to layer 2. Continue. Now we want to get rid of this one. So I click on node region. We can put it on cell. Select this one and remove selected. We click on somewhere here to reset that and put it on all and select this surface. So at this time, layer 1 is master and the bottom of layer 2 is the slave. So we selected and now we want to go to the node region. We reset the view, put it on cells, select this one, this one, this one, and this one. Now this time we want to replace selected. By holding Alt, Control, and left click, you can select this bottom part and click done. Okay, now we tie these layer 1 to the substrate and layer 2 to layer 1 to create interaction. Okay, everything is done here. Now it's time to go to the load. From load manager, this time I want to change all the loads to the body heat flux. So I want to delete them all. So in that case, I would like to open the model tree here, and from load, I can select them all and say delete. Now I want to create 8 loads. Here, create load 1, step 2, body heat flux, continue, and I want to select this cell. Scroll button. This time I want it to be 3E10 and this one should be analytical field 1. Okay, now we have the load here, inactive. For the next step, now we want to create all the same for the first layer. So we created 4 loads here. Now it's time to create a datum point for this one and the local coordinates and the analytical field as well. So from tools, datum, midway between 2 points, select these 2 points and it's created. Now these 2 points, it's created again and done. Now we want to create local coordinates. I select this one, create datum, click on create datum here, continue this one, create datum, and do it again. Okay, now we have the local coordinates for the second layer. From here, fields in the model tree, we have different analytical fields. We want to copy them. So this one is 5, and we edit this one, and instead of that we want to select this one. Now we copied this one and change it. Okay, we want to create more. Okay, we created all the analytical fields. So if you see here, this one are for the second layer. Now it's time to create the loads. Here we need to create load 5 body heat flux, but this one should be step 7. We select this one and done. This is the same 3E10, but this one should be analytical field 5. So we create other loads for the second layer, and it should look like this. So we double check. This is load 1 from layer 2, and it should be this one and this one. Oops, this load is not deactivated, so just to make sure, yeah. Okay, now everything is done. It's time to go and submit the job. So we create a job. We have to make sure that the job is in model 2, and we name it 2 layer SLM, and okay. Now I come back after the job is completed. The job is now completed. Let's take a look at the results. So I want to put this on nodal temperature. Let's put it back here and adjust the animation speed somewhere around here. See how it goes. Yeah, it looks fine. Now this is the end of layer 1. It cooled down and starts the new layer. I stop the animation here. As we see, it cooled down to the room temperature. Easy as that. We could simulate a multi-layer additive manufacturing. Now you feel free to go and create more layers to see how it goes. Other thing that we can do is to go from XY data, ODB field output, and here we can have it on unique nodal temperature 1,1, and we can, from here we can select selected frames, and let's go to the last cell of the first layer, like somewhere around here. We can select this one and add this, and we can go to this one, select this one and say add selection, and plot them to see how it goes. Yeah, as you see here, due to the accumulation of the heat, we have higher heat in this one compared to the first layer, which makes sense. And if you want, you can go ahead and select the parameters for the next layer. Most of the time they print the second layer with different parameters, so feel free to change the load and modify the result as you want. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In additive manufacturing, every thermal cycle leaves behind a hidden signature, residual stress. If left unchecked, it can cause warping, cracking, and mechanical failure. But what if you could predict and control it with precision? In this tutorial, I'll show you how to extract and analyze residual stress directly from your thermal model in Abaqus, giving you tools to optimize your 3D printed parts like a pro. Let's get started. Alright, the first thing we should do is to go to the working directory and opening the CAE file. we have the model here. If you remember the last time we simulated this 2-layer additive manufacturing, so if you haven't watched that video, you should watch that video. Okay, so the model 2 is the model we simulated, and this is the job. I'm going to look at the result, and we need to put it on nodal temperature, and as you see, the layer is cooled down to the room temperature, while the substrate is already 172 degrees centigrade. So we need to increase the cooling time in order to make sure that it reaches the room temperature. Then we go to the step, and here the last one is 100. I put a very high value such as 2000 and click on OK. We don't need to change anything else, and we need to submit the job. It's recommended to have another job, for instance, multi-layer, longer cooling. Okay, we submit the job. If we hit OK, we monitor the job and we wait for the job to be completed. So the job is completed, but before we go to the result, if you're enjoying this video, I'd really appreciate it if you could leave a comment. It's completely free for you, but it really helps me out and keeps me motivated to make more content. Okay, we go to the results. This should be nodal temperature, and this is the final cooling. As you see, it is 25 degrees centigrade. This is what we want. Alright, now we can jump back to the part, and here we need to copy the model and we name it Residual Stress, and we click on OK. From now on, every change we make is in this model, and make sure you double click on it. It should be an underline under the model name, so we make sure that we are in the residual stress. First things first, we need to modify the materials properties. So I go to the Inconel, edit. We need to add mechanical elasticity, plasticity, as well as the thermal expansion. Starting with elastic, you should check this one, use temperature dependent data, and I have an Excel file containing all the data, and if you need this Excel file, just let me know in the comments, I can send it to you. I select this one, Control C, and here Control V, we have this one. Now from mechanical plasticity and plastic, we use temperature dependent data, and here Control C, we go to Abaqus and Control V. Next one is expansion. So you can either use the subroutine, or in this video, because it is simplified, we don't need a subroutine, and we only copy paste this value here. This is OK. Now we go for the layer and we do the same thing, mechanical elasticity and elastic. This should be here. We check the use temperature dependent data. Now it's time to go for the plasticity and plastic, and this one is here. Control C, and it's done. And mechanical expansion, temperature dependent data, the expansion is right over here. Okay, now we are finished with the materials properties. Let's go to the step. Here we need to remove all of these steps. So by holding shift and clicking on the first one and last one, we can delete them, because we need to create static general steps. It should be static general, as I mentioned before. The time must be 20,020. This needs to be 10 million, so basically 7 zeros. 1 2 3 4 5 6 7. The initial 1A-5. I copy and pasted this one. 1A-30, and I put this one on 500. This is the step we wanted. Another thing is to go to the field output and edit. We only need the stresses, so we don't need the displacement, we don't need the force. Here we uncheck everything because we don't want to have too many files, so we only need stress. The step is done. Now let's go to the load and boundary condition. So here in the load, when you go to the load, you don't see the previous data here. Then we don't have any boundary conditions here, but we have the predefined field. I'm going to create a new predefined field. So here, predefined field 2, step 1, other, and it must be temperature. And we continue selecting everything, and we click done. But here, instead of direct specification, we need to use from results or output database. So I need to open the directory, and this is what we have: multi-layer longer cooling. If the characters of the path and the file name exceed 80 characters, you're going to have a problem, so you basically need to change that. Alright, begin step is 1 and the end one is 11, and mesh compatibility must be compatible, and we click on OK. So we basically reading the files from the ODB output files from the previous simulations. So we need another thing here, which is boundary conditions. I want to create one boundary condition in the initial step from here. So we can rotate this here and we select this one. And let's say we have to clamp them. We encast the bottom part totally, or if you have the welding, you can clamp only the corners. And this is also done, and we should go to the mesh. Make sure to change the element types. So we click on this one. Done. Now it needs to be standard 3D stress. We go to the substrate, this one. We select everything. Done. 3D stress. Everything looks good. Now it's time to create the job. I want to name it Residual stress. Remove the space. Continue. OK. Now let's submit the job. And the job is completed. Okay, let's take a look at the results. This is the residual stress we have here, and to be fair, it's really high. 796 megapascal is really high, and here we have the highest in the center, which is in the layer. So let's go to the contour option and the maximum and have the show location, and you see this node has the highest Mises stress. Now what matters for us is the S11, which is in the X direction, and S33, which is in the Z direction, also known as transverse and longitudinal stresses. So let's take a look at S11, and this is the maximum location, is somewhere inside the layers, one of the layers. And this is S33, which is right here. Now we want to create a path in the longitudinal direction and one path in the transverse direction to see how it goes. So from tools, we go to the path manager and we create. First we go for longitudinal. Continue. We can have viewport selection, add after, because we want to select them from here. Let's create something from here, here, and here. We carefully want to select it. Now we rotate it here, have them here. This can be okay for the path we want. We click on done and okay. Now create the transfers. Now please continue and add after. So let's create it from here. It's completed by going through the end. Now it's okay, and we click on OK. Now it's time to plot those. So from create XY data, we go through the path and we want to see the transfers. Okay, this is the transfers one, and let's plot this. As you see, it looks like the typical residual stress curve. So if we just open two random papers, we can see the same thing here. For instance, this is the residual stress they did have, or I can pop up another one. You see here, this is the typical of residual stresses, and we also can have S11 here. We can apply okay and plot. This is what we have in S11, and we also can have the Mises stress, which looks like this, and we can have the longitudinal one. We plot them. As you see, there's something like this. The shape is not ideal, but if we define the path accurately, we can have a better thing here. So the field output, we can have S11 and plot. This is the S11. As you see here, goes down. What is clear in this scenario is that the curves follow a similar trend. Just keep in mind this Abaqus tutorial is for educational purposes only and doesn't include validation or comparison with the article. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. In this video, I'll walk you through arc-based additive manufacturing simulation using the Goldak DFLUX subroutine. In Abaqus, we'll simulate a moving heat source to model the wire arc additive manufacturing process step by step, including how to define the heat input, mesh the part, set the boundary conditions, and interpret thermal results with full thermal history. This tutorial follows a clean and reproducible structure, so whether you're building a thermal model for academic research or thesis work, you'll walk away with a working debug DFLUX setup. If you ever struggle with getting DFLUX to behave correctly or want to simulate wire arc additive manufacturing accurately without trial and error, this video is for you. As always, we start with creating the part. So hit this one. Part 1 should be substrate because we want to create the layer separately. Should be 3D deformable solid extrusion, and this guy should be 0.2. Continue, and we need to create a simple rectangle just like this, and we select the dimensions 0.0025, and this guy should be 0.05, so enter, then scroll button, done, and this should be 0.05 and okay. Now we have the substrate. So what we can do here is to select the path of the DFLUX or where we want to put the layer on. So select on this one, partition face sketch, select this face, then done or scroll button, then this one. Now you need to select these two lines, scroll button, then this one, scroll button again. We need to know how much is this value, so it's 0.004, and okay, done. And we have these two lines. Now we want to extrude them toward this direction. For that purpose, left click and hold, then you need to sweep like this. You can select this line and hold shift select the other one. If you're using older versions of Abaqus, like Abaqus 2017 or Abaqus 614, you cannot select both of them. So let's do it that way. Select this one and sweep along edge, then select this edge and create partition, then select this one, done. Select this line, done again, sweep along edge, this edge, and create partition. But in Abaqus 2024, you can use them at the same time and extrude them, so it makes your life way easier. Anyways, let's create the layer. So we name this part 2 as layer. It should be the same, 3D deformable solid extrusion 0.2, and we need to create a rectangle again. So this should be roughly the same, but the thickness is different. It's 0.02. This one should be 0.05 again, but this one should be 0.04. So now we have the layer. This is the substrate and this is the layer. Okay, let's go to the property. To make your life easier, I uploaded the materials property in the feamaster.com website. So if you go to the shop, material property packs, and here you can select the temperature dependent properties of carbon steel, add it to cart, go here and do the checkout. You can download that for free. After you filled everything, you can download the temperature dependent properties. So let's open it. Here we have different things. Let's go to the Abaqus. The material is steel and we need thermal conductivity, we need thermal specific heat, and we need general density. So all of them should be temperature dependent data. So from here we should find density. The first one is the density. So Control C to copy and literally paste it here, then go to the specific heat, use temperature dependent data and copy paste this value here, and for conductivity use temperature dependent data, and this is the conductivity. Place everything here and okay. Now it's time to create sections. So we need one section for solid homogeneous and the material is steel. Now we need to assign the section here, done and okay. Now we need to do the same thing for the layer. So we just need to assign the section here, done and okay, because we assume that both of them are having the same materials. Okay, now it's time to go to the assembly. We need to assemble both of them and make sure that it's part dependent so that we can mesh each part dependently, and okay. Now we need to put this one from here. So we select this one to here. Now we have one substrate and we have one layer. Okay, now let's translate both of them to here. So select both of them and okay. Then we need to translate this part to here. So it's better to translate them once more. So we select them both and we select this one and select this one. The reason behind this is to define the 0, 0, 0 as the starting point of the flux, and it's easier to do that. You can do that without that, but you have to find this point as a starting point. So as we want to make things simple and starting with the 0, 0, 0, we translate this to here. Okay, we're done with assembly. Let's go to the step. Before performing any action, let's go and save the file. So I want to save this in a folder. Like I can create a folder like wire arc AM and okay, and I can name this wire arc additive manufacturing, then okay. One more thing to do is to go from file and set the work directory to the specific folder. So in this case, every file we create, including IMP file, the jobs, and everything else would be stored in that directory. So to select that, we go here and we select the wire arc AM, and so we need to select wire arc AM and okay. Now as you see, it's C, temp, and wire arc AM. So if we click OK, from now on we can find the files easier. If you like this trick, please like the video to continue. Alright, let's create the step. Create a step. It comes after initial. It should be heat transfer. The time period can be 25. This one can be 1 million, so it is 6 zeros. Initial can be 0.1. This one can be 1e minus 10. This one can be 1. And this one should be 350 and okay. Then we go here to the field output manager. Then we create this one. We don't need the RFL or we don't need the HFL. We only need nodal temperature. Then okay, dismiss, and we're done with this step. Let's go to the interaction. Okay, the first thing to do is to create a tie constraint. We want to tie this layer to the substrate, so we name it tie, continue. So select node region, and we need to select this one. So go from here, create a display group, put it on cell, edit, select this one, done, and remove. And we select this one, done. And now we need to select the node region again. So replace all, select this one again, cells, edit. You select this one, hold shift, this one, and done. Now we remove them, dismiss, and you can rotate the instance and press this one, select this one, and done. Let's put this one on this and replace everything. So we have the main surface and the secondary surface, and it's okay, done. Now as you see, the interaction is created. Now it's time to create the interaction properties. So we need to create the surface film condition, continue. First we select everything, then we rotate it using Control plus Alt and left click, or you can use this one. If you don't click anything on it, it shows you can hold Control Alt and mouse button 1, which is the left click. So by holding Control, you can deselect these parts, so we don't need the bottom part and we only need the surface, and done. Now we need to create surface film coefficient. It should be the property reference, and we need to create the material property. So from here, create interaction property. It should be film condition and continue. Use temperature dependent data and go back to the Excel file, surface film coefficient, Control C, come back here, Control V, and okay. This was the property of air. So if your model is in water or anything like that, you should use another interaction property. So this is selected. The sink temperature can be 25 and okay. Now we need to create another interaction. So from interaction here, we need surface radiation and continue. Then again, we select everything, control, hold control and deselect this one and done. Let's put it back here. The emissivity must be 0.49 and the ambient temperature is 25. And okay, as far as I'm concerned, we've done everything in the interaction. Now it's time to go to the load and boundary condition. This is by far the easiest part, so we need to create a load here in step 1, and it should be body heat flux because it's wire arc additive manufacturing and we want to use Goldak model. If you want to use a surface heat flux, you need to create a subroutine for Gaussian distribution. This is the body heat flux, continue, and we need to select this one, done, and we put the magnitude of 1 here. And instead of uniform, you select user defined, so it says you need a user defined subroutine DFLUX, and okay, now it is created. Now one more thing to do here is to create the predefined field. So we need to select step initial, and from other you need to select temperature, select everything, done, and it should be 25, which is the initial temperature, and done. Now we're done with the load. Let's go to the mesh. Meshing is very important, so attention please. By the way, if you enjoyed this video so far, please share your feedback with me in the comments down below. It's totally free for you, but it gives me the motivation to continue and creating more videos like this for you. Thank you. Now we go to the part. First we go to the substrate. Okay, now we want to see the edges. First we select this one, hold shift, select these 4, these 2, and these 2, done. Put it on by number and add a 0 here, so we need 40 elements on this direction, and okay. Now let's select others like this one, this one, this one, and this one, and done. This should be 6, and okay. Now you need to select every line parallel to this one, like this one here, 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 and here. Okay, done. This should be 4, and done. Let's mesh it. This is the mesh. As you see here, we have a refining version in this direction in the middle. Now let's go to the layer and do literally the same thing. So this one, this one, this one, and this one. These should be 4. This one, this one, this one, and this one. They should be 6, and last but not least, these guys must be 40. And if you go, oops, now you need to mesh it, and if you go back to the assembly, you see that all of the lines are matching here and here, and if you rotate you can see the lines are matching here, and if you go the other side you see everything are in line. So it's very important to do such a thing. If not, there would be a mismatch and it reduces the accuracy of your model. Okay, one more thing to do is to go back to the part, assign element part, and this should be heat transfer. Then okay, now we go to the substrate and we should select everywhere, and this should be heat transfer again. Now we should go to the model, and from edit attributes, model 1, we should define the absolute 0 temperature minus 273.15, oops, 1 and 5, and we need to select Stephen Boltzmann. This should be 5.669 E minus 8, and OK. Now that we selected everything, let's set the global size at this one. So if I OK and mesh it again, let's go to another one, the substrate. Let's put this one on 20 and auto delete the mesh, and as you see, the mesh is now in a better position. We go to the job. Now it's time for the subroutine. Okay, now I open the Visual Studio 2022. So we go continue without code, and from here file, new, and file. I want to create Intel Fortran and .4 file. I open it. Now this is the file I have. Now we need to go to the Abaqus documentation. Now here in Abaqus, if you go all the way down to the user subroutines, and we need the Abaqus standard user subroutines and DFLUX. This is the code for the DFLUX, so I always recommend you to copy and paste it from here. Don't trust any other sources. Then you go back here and paste it. As you see here, we have subroutine DFLUX, and here is where we need our code. So this is the code. We have the coordinates X, Y, Z, and we have the heat source center. We have X, Y, and Z here, but for XC we have X0 plus V, which is the welding speed, times T. So in this manner the flux would move. And here we have the Goldak parameters. So these parameters are for the ellipsoid A, C, PF, PR. If we take a look at this image of the Goldak double ellipsoid, you see here we have the front and the rear ellipsoid, and we have A, B, and C. So as our coordinates are not the same as this one, we have two B's. So here we have PF and BR, and we have A and C, and this is F for front and F rear, which is one coefficient, and the summation of these two coefficients should be 2. So if we take a look at this article and we go all the way down to these equations, we have this equation for the front and we have this one for the back. Actually the front would passes through the temperature and the rear ellipsoid maintain it. Here we have for the x bigger than 0, and here we have this one for the x's less than 0. And this is the fraction FR over BR and FF over BF. And as you see here, the FF plus FR must be 2. They also provided the table including A, C, BF, and everything else. I took FF and FR from them, but I wanted to have my modified version of the A, C, and BR. In other words, the ellipsoid, so I changed the numbers. You are allowed to change the numbers for your model as well. So let's go back to code here. We have the heat input parameters. The eta here is 0.8 V I, so basically we have the Q out of it. And here we have the QR and QF. Let's go back to the paper to see that. Here actually this is the part before the EXP term, and we have this one. So this is the equation for that, QR and QF. Here we have the rear half. This is the code for it. If the X is less than or equal to XC, we would have this one. And as a result, the flux would be this one, QR times the EXP. We basically put the equation of the QR here. And we have an end if here, and there's an else if here. If X is greater than XC, we will have this equation here for the flux, and the flux 2 is 0. You might wonder what this and would be. So if I cut it and paste it here, you see it turns into a comment and it cannot fit there. So we put it here and we place an and, or we can place one, or we can place a star here in order to define that this is the next line in continue of the previous line. And that's pretty much everything. If you need the code, just visit the website. I put the link for you in the description. Alright, we save this one and we go back to the Abaqus. Now we jump back to Abaqus to create a job. So I would name it Wire Arc Additive Manufacturing and continue. And if we go to the General tab, here it says user subroutine file. As we set the work directory here, it would open the folder, and this is the Goldak .4. And okay, we can have the parallelization here. Let's put it on something like 8. And okay, now from here I would like to submit the job. We ignore this one and submit and wait for it. And as you see, the job is completed. Let's go and take a look at the results. So if I put it back here, first you can see that manually, as you see here, the flux is moving, and because we tied the layer to the substrate, you see the gradient of the temperature on the substrate as well. If you don't tie them together, you only see the temperature gradient on the layer. Okay, now as you see, it's moving. You can also put it back somewhere around here, and from here you can specify the limit. Let's put it on, for instance, 2500. In this case, you can see that better with the animation, I mean. Yeah. You might need to modify the ellipsoid parameters yourself. So this video has the educational purposes and we're not validating it with any experimentals, but most of the users first they run the job and then adjust the parameters to match. Okay, now another thing we can do is to go from here, ODB field output data, continue, and we can put this on unique nodal and nodal temperature element nodes, and we can edit the selection. We can select some nodes, for instance one here, and we can go through the thickness like somewhere around here, 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 here. Maybe it's better to select these two and not this one. So if you want to plot them, you see here we have the temperature versus time plot for different nodes, which is pretty common. And if you want to save your data, here you can right click on this one and edit, select all of them, or select the first one, go all the way down, hold shift, select the last one and copy that. And if you go to an Excel file, you can literally paste it here and you can plot them yourself just like this. And as you see here, we have the plot of time versus temperature. You can modify everything yourself, I mean the axes or the legend. Let's jump back to Abaqus. If we go here, we can also make the animation better or make the view better. If you hit this one and put it on feature edges, you don't see the meshes or the nodes, and it's more beautiful. Yep. And another thing we can do is to cut. For instance, here we can cut it to see how far it went, and you can, if you want to see the values here, you can go from here, and from probe values you can put this either on elements or you can put this on nodes. And if you put it here, for instance, if you click, it collects them and you know the nodal temperature here without plotting. You can move and track like this. Yeah, as you see here, it differentiates them. So we have layer here 2700, and in the same position the substrate is 1000. Thanks for watching so far. If you are enjoying this tutorial, don't forget to drop a like, or if you have any question, just ask me in the comments down below. I respond to every single one. Thank you. Watch this video as I show you the best way to simulate selective laser melting in Abaqus. This isn't just another generic walkthrough. I'm going step by step with zero skipping, no unnecessary talking, and straight to the point. You'll see exactly how to define the laser path, apply the heat input properly, assign temperature dependent materials, and track the full thermal history of the part. If you've been stuck messing with subroutines or guessing how to model the thermal side of metal 3D printing, this is the cleanest, most reliable setup you'll find. Let's jump in. In this tutorial, we use the previous simulation files, but we only changed the load. Now it's time to define the load, and by far, this is the easiest part of this tutorial. First thing first, we go to the predefined field, and in the initial, we would go to the other, and we should select temperature. We select the whole model, done, and we input the value of 25. By doing this, we assume that the initial temperature of the model is 25 degrees centigrade. Now it's time to create the load. We go to the step 1, thermal, and as we're doing the laser-based additive manufacturing, we should select surface heat flux instead of body heat flux. Okay, we select this surface as we want the flux to move from here to here, and done. So instead of uniform, we should select user defined, and as you see here, there's a node coming up. User subroutine DFLUX must be attached to the analysis job, and we can either put the value of 1 or 0 here. So as you see, the load is created. Now it's time for the subroutine. Okay, now I open the Visual Studio 2022. So we go continue without code, and from here file, new, and file. I want to create Intel Fortran and .4 file. I open it. Now this is the file I have. Now we need to go to the Abaqus documentation. Now here in Abaqus, if you go all the way down to the user subroutines, and we need the Abaqus standard user subroutines and DFLUX. This is the code for the DFLUX, so I always recommend you to copy and paste it from here. Don't trust any other sources. Then you go back here and paste it. As you see here, we have subroutine DFLUX, and here is where we need our code. Okay, I zoom it out to let you take a screenshot or write it down yourself. I'm going to talk about it. Here we have the coordinates. Coords 1, 2, and 3 are X, Y, and Z. Accordingly, time 2 is the actual time step we have in the module of a step. So time 2 is the step, and this is T. We have X0, Y0, and Z0. So I don't need the Y0 here because we're only working with the X and Z. We have the laser speed, V. We have the power, and we have the radius of the spot. So imagine if it's a laser, this would be the radius of spot. And we have the famous pi 3.14. Here in this section we define the movement. The Z is Z0. It means we don't move in the Z direction, but we move in the X direction with the speed of V in the time of T. Okay, this is our model. We don't have any movement in the Z direction or Y, but we only move in X direction, just like this. Okay, here is the Gaussian surface heat flux we have. R02 is optional, but it makes your coding easier. So instead of writing R0 to the power of 2 here, or here, or here, you just write it down here. And we have the distribution here, which is the equation. We have x minus xc to the power of 2 and z minus zc to the power of 2. And here we have the q, which is 3 times q pi and so on. I wrote down the equation here. This is the Gaussian distribution. Q 3q over pi r2 exp of minus 3 times x minus xc to the power of 2 z minus zc to the power of 2 over r2. So it should be the center of the torch and decays rapidly with the distance from the center. Basically, this model is a Gaussian distribution, that is a fancy name for a bell curve, a smooth symmetrical peak that rapidly falls off as you move away from the center. The equation would be something like this. We have the power, we have the exponential part, and here in the beginning the flux one is 0. Then we wrote down the f here. And why did we write down the f here? Is because this is a cutoff check. In this manner, we would like to save our power. Instead of running the whole simulation in the whole model, when it's greater than R0, we don't need the calculation. So we write down this if to make that happen. And if you wonder why I use LT here, it means less than. So if the distance to less than R02, then the flux one is Q0. And we don't have the flux 2, or you can write it down something like this. If x minus xc to the power of 2 z minus zc to the power of 2 is less than r0, or you can say dist 2 less than r0, then whichever is easier for you. Okay, we want to save this one. Make sure it should be deflux.for. If you guys don't have the Visual Studio, you can open this file with Notepad. And here I can, for instance, modify the Q. And we can change this, for instance, to 600, which is more realistic, and file and save. Now we go back to Abaqus to create the job. Okay, here is the job. Create, we name it SLM DFLUX. And hit the continue, and from general user subroutine file we need to select, as you see, our folder is here, and we can select the deflux.for, and with parallelization we can put this value on 8, and we hit the OK, and now the job is ready to be submitted. So we hit the submit button. We ignore this one, and I'll come back after the job is completed. Now the job is completed. Let's take a look at the results. Yeah, here it is completed. Let's go for the results. I put this one on the contour, and this is the final step. Let's put it all the way back here and start the animation. And as you see, this is the laser spot moving. Because we created an interaction between the layer and the substrate, there's a temperature gradient here. I believe that this is the maximum speed. Yep. There we go. It goes all the way down to here, and the process is finished. We can, for instance, put this one on limits here. We can have a limit of 2500, and here when we move this, you can see the flux better. Here, this should be the melting point of your alloy most of the time. but it's totally fine. Yeah, this is the movement of the flux. And one thing we can do is to go from XY data, ODB, field output, continue, and here put this one on unique nodal and nodal temperature. We can select some elements or points, for instance this one, and we can select this one. We need to hold shift to select the lines like this. We need to hold control and select the points like this or this, and we can plot them. So this is the plot of 5 nodes, temperature versus time, and here from the XY plot we can go edit, and we can select them here by holding shift. You can copy them and paste it in an Excel file and plot them yourself. One other thing we can do is to go to the comment option and put this one on free edges, and okay, and now it's more beautiful. It's more suited for publishing articles and stuff, and you can see them without the nodes. And if you go to the viewport and annotation option, you can set all off and only leave the legend. So this is, in this case, we get rid of the state blocks and stuff, and we can take a look at the results. Unlike the Goldak DFLUX model, we only have a surface DFLUX here, and if you take a cut, we don't see a penetration of the flux through the thickness, but we have a temperature gradient. But for the DFLUX of Goldak model, it's totally different. And that's it. Thanks for watching. If you found this helpful, please smash the like button and subscribe to the channel to see more videos like this. Don't forget to watch the video on screen before it ends. Stay tuned.